Today we are going to do chapter 8.1. So first let's scan the book. This was already scanned last time, but I guess I will check it anyway. So this is the previous part, and then this is the next part. And let's see. Okay, that should be good enough. Next, page 258 and 259, which is right about here. That's the whole page. And then a little bit closer on the top. And a bit closer on the bottom. Okay, that should be good enough. Next, page 260 and 261. Let's see here. The whole page. Okay, and then a little bit closer on the top. No. Let's see. I need to get this thing to be parallel. All right, and then the bottom. That should do it. And finally, page 262 and 263, the homework page. All right, let's see that. Does that look okay? All right, and then a bit closer on top. Why is that thing? No. Well, anyway, and then closer on the bottom. Okay, so that should do it. All right, so let's start on page 257, where we are, in this chapter, we're talking about limits. That is, when we do a limit like this, especially when f and g are both 0, we have a 0 over 0 situation, okay, which we have, which we covered in basic calculus. So, this, please read this page yourself. It's a review of what we did back in the day, okay, and turn to the next page. And more examples, okay, of what we did. For example, you might remember this trick here. If you had a square root situation, then you multiply by there's a name for that thing. What is it called? Whatever. Anytime you have a radical, you multiply by the plus version if it's minus, and so on. And then you turn it into something which works much better. And with that trick, you're able to find the limit. Okay, that otherwise it would have been 0 over 0, and we have no idea how to do that. Now, so then, and here are some examples we have where 0 over 0, the limit can be really various. Well, there's just some examples. Okay. Now you might not remember how to do these, so please redo these things yourself. Well, redo this one too, but redo these things and figure out how they are done. Now I did it right here for your reference. These problems are not necessarily obvious how it's done. Okay, it might take you some thinking or even digging it out and looking at the past stuff. But anyway, so here is what I have. The limit of sine x over x was proved in calculus 1, and then we use the squeeze theorem, and it's proved by area. Okay, here's the details, and I copy and pasted this from AI, and how the sine x over x is proved without L'Hopital's rule. Okay, and then the other one, which is the limit of 1 minus cosine over theta squared, is proven from this problem, which once we know what this is, then this one it works in a similar way, and then we can calculate it to be well, anyway, it equals to whatever. And similarly, this particular limit is calculated by its definition. That is, this thing is f prime of 1 if f of x is natural log of x. And finally, this limit is calculated as the definition of f prime of e of x as 0. Now that is, those are the four limits. let's see. Give me a second here. So next, let's look at subsection 1.1 on page 258, where we are going to consider yet the law of the mean. The limit is that we are considering the fx over gx, especially when the result is 0 over 0. There is no way to really tell where it goes. For example, we consider these four limits. Please verify this yourself, okay? Sine square x over x is 0. And that's because sine x over x equal to 1, okay? And sine square x over x squared, then it's just 1. And then if you have too many x's on the bottom, then it goes to infinity. And then if you have some more complication, this is the same as sine x. Why do I have sine x on the top? I mean it on the bottom. But anyway, yeah, switch that around. I will fix it now. Okay, I fixed that. Now the last one, you notice that the sine x over sine x, that goes to 1, and the other part, sine of 1 over x, that goes nowhere because that just wobbles forever. Okay, as x goes to 0, 1 over x goes to infinity, and sine just keeps cycling itself. So it's going to go do that infinite wiggling thing, and therefore the limit does not exist. And the two in non-existence are not quite the same. Okay, this we know the limit went to infinity, so it went somewhere. We just can't catch it. But this one, it doesn't even go anywhere. It just keep wobbling back and forth. It doesn't ever stop. So it's not even going to infinity. But so let's look at theorem 1. Okay, theorem 1 have f and g equal to c is in C1 continuously differentiable, as fc and gc equal to 0. And then g prime of c is not 0. Now notice fc equal to gc equal to 0. The c cannot be at the end point. Okay, and so anyway, continuing, g prime is not 0. And then if these conditions are true, then the limit of f of x, g of x, as x goes to c, is equals to f prime of c over g prime of c. To prove this, we're going to use the law of the mean. That is the MVT, which is on page 10, which we have looked at many times, but we're going to look at it again, okay? Because the MVT is extremely useful, and we use it all the time, so it doesn't hurt to take another look. This is the MVT on page 10, right here, okay, the familiar thing. And where we have FC plus FC plus H minus FC is equal to the H, that's the difference, times F prime of C plus theta H, where theta is between 0 and 1. So somewhere in between, we can pull the derivative out times the H, etc. And that's the difference. So applying that theorem here, we will have this part at the bottom. We have f of c plus h, okay, which equals to fc plus h minus fc. Why is that? Because fc is 0. We said so. Okay. Similarly, gc c plus h is the gc plus h minus g of c, as g of c is given to be 0. And that, applying the MVT, we got that f prime business. Now in this case, then we have two thetas, okay? The two thetas both between 0 and 1, but they may need not be equal. They're just applying MVT to each individual thing. All right. So we got here, and we're already looking very good, right? Here are some details that we should mention. H is chosen such that C plus H is still within A and B. H is cannot be 0, and then G prime of C plus theta H is not 0. That's because G prime isn't at C is not 0. So if it's close enough to C, G prime wouldn't be 0 either, because G prime is continuous. Yeah. Continuing. So, and then next on the following page, to page 259. So as a result of it, then being that g prime is not 0, in the little right next to it, that means that, well, g of c is 0, means that g of c plus h cannot be 0, okay, because it moved over a little bit, and the g prime is not 0 in the immediate neighborhood. So it can't be both, and it can be both 0. So then as a result, this equation makes sense, okay? We're not dividing by 0 here. And so now that the equation makes sense, then all we have to do is just cancel out the h. and then let h goes cancel out the h that's being multiplied. Let's get rid of that, the h at the end, and then let the h inside go to 0. Okay, then we got the equation, let all the h's go to 0. Then f of c over g of c will be equal to f prime c over g prime c, which is just what we are trying to prove. So the theorem comes out very nicely. Now, and then, so next part is considering that if g prime of c equal to 0, let's see. Okay, now if g prime is 0, but if g prime indeed is 0, but at least f prime isn't 0, then the limit will just go to positive infinity if we slap the absolute sign on. Without the absolute sign, then you have to be careful whether it goes to the positive or negative infinity. So the next thing we need to let's look at the next example here. Okay, where let's see, please do this example where as x approaches 0 plus, that goes to positive infinity. And if x approaches 0 from the minus sign, then this thing goes to negative infinity. But if you slap an absolute value on it, then of course it goes to positive infinity. And if f prime c and g prime are both 0, then we can't. This doesn't do anything. But the point is that even the theorem 1 requires that g prime of c is not 0. But even if it is 0, we still might be able to get things to work, is what that means. So next, we have a bunch of examples in the book. Please do all the examples yourself. Okay, they are mostly from Calculus 1, and so it's a bit of a review section, which doesn't hurt. So please do some of these because we're going to be working with limits. So it's good to refresh your memory on how the stuff is done. And there is, and I have done it. I did it here for your reference. Example D, what? Okay, I better find it first. So starting at example A, which is right here. Okay, starting at example A, they're pretty straightforward. Example B, okay, please do this yourself. And then example C, example D, and then example E isn't even 0 over 0 format, I think, or something like that. Or was it example D? No, D was not 0 over 0 format. E was, well, whatever E was. The point is, please do all of those and read the book's comments on each problem, and just to refresh your memory on this type of thing. Okay, so that's that. Next. So next, we are going to consider the case where f prime of c and g prime of c are both 0. Now, earlier we have mentioned right here that if, where is it? Right here. If f prime c and g prime c are both 0, then theorem 1, the one we just proved, is not applicable because it requires g prime of c to not be 0. And f prime of c, well, anyway, it's not, at least g prime of c to not be 0. So to prove that, let's go to the next page. So let's look at theorem 2 on page 260. The theorem 2 says f and g are in C1, okay, and then c is between a and b, and then c plus h is also between a and b, and then we have this new equation to be true with those conditions. That is f of c times g f. The difference of f times g prime is equal to the difference of g times f prime. Now this is similar to the previous theorem, except that things are not written in division form. Okay, there is no fractions here. Because the previous one that we just did, things are written in fractions. Now we are doing cross multiplying. The reason for that is we don't know if any of these things are 0, so we cannot divide them necessarily. So to prove this, and I should mention that I think later we will also show that this theorem it works. It doesn't. These two things don't have to be C1. If they just exist, that is good enough. But we'll prove that later. I just wrote this down as a sort of a reminder. So C1 is not absolutely necessary. But anyway, so for now, let's move on to prove the theorem. Okay, to prove the theorem, we're going to use a trick. Okay, there's always these neat tricks, and so we're going to use this neat trick where we're going to define something called phi of x and defined as the determinant. Okay, where we have f of x, g of x1, the first row, f of c, g of c1, second row, and f c plus h, g c plus h, and 1, third row. So we have a function defined, okay, and you might think, okay, what about it? So the next step, we're going to calculate what phi of c is and show that phi of c is 0. How do we know that's 0? Because if you plug in phi of c, the only place where you can there's an x in this is just the first row, right? First row has x's. The other rows only have c's and h's. So if you plug c in here, then you notice the first row and the second row are identical. And when it comes to determinants, if you have two identical rows, that means the determinant is automatically 0. That's just how that stuff works. So then, therefore, I have just proved that phi of c has to be equal to 0. And then next, let's calculate phi of c plus h. If you plug c plus h in the x's in the first row, that's the only place where there is an x. There are x's, right? So once you replace x with c plus h, you notice that the first row and the third row are identical. As a result, phi of x is the determinant equal to 0 again. So as a result, phi of c and phi of c plus h are both 0. And so this function has a point 0 here, equal to 0 here, and also equal to 0 over there. And so we're going to apply something called the Rolle's theorem, which is on page 9. That Rolle's theorem is an earlier form of the MBT, okay, and we still use it once in a while, and this is from way back when. So let's look at it. Rolle's theorem states that that we have f of x is continuous, and f prime exists. Okay, it just have to exist, and the two endpoints are 0, which it is. For our phi of c and phi of c plus h are 0. And that would mean, here's the proof, then the function is equal to, the derivative of the function is equal to 0 somewhere in between. Okay, that is Rolle's theorem. So that is what we have right here. So by Rolle's theorem, then there is some kind of a value in between. Okay, phi of c plus theta h, whatever, where theta is between 0 and 1, such that phi prime of this value is going to be equal to 0. And so the next step we need to calculate is what is phi prime. Phi prime, normally phi is defined in terms of some kind of determinant, and normally determinants multiply each other, right? And then we have to be careful that we need to do the product rule. But in this case, only the first row has any x's in it. Okay, and our derivative is taken with respect to x, and being that only the first row has x's in it, so we don't have to worry about the product rule. We can just slap the derivative symbol right on top of it. So phi prime is simply replacing this with f prime c plus theta h, and g prime the same, and everything else stay the same. So this thing still holds. All right. So far so good. Okay, and but watch out that this thing becomes 0, because that thing when you calculate it is that times these things, right? And those are all constants for the sake of in the differentiation. So that all that gotten rid of. That's why that number is 0. So that part you have to be careful about. So it's not just a matter of taking changing the f's differently, but the one that doesn't end up multiplying by x, then you have to reduce it to 0 there. Or if what I just said doesn't make sense, just multiply this whole thing out and you will find out, like I did. At first I didn't think of just doing it like that, so I multiplied everything out, okay, and everything worked out the same way. Here's phi prime, which equals to that, and which equals to this. Now the last step is that now we do need to multiply it out. That is phi prime equals to this stuff, and here's phi prime x, and then plug all the stuff in. What is that? that is, if you rewrite this equation, that is exactly this equation, and this equation is exactly what we're trying to prove. So once you, that is, this thing, once you multiply it out, is exactly this thing. Okay, that is what we're trying to prove here. So please do that yourself, like I did, and then you will see why that is the case. If you don't write it out, it's kind of confusing and hard to see, I'd say. Right here, I think. Yeah, here's 5 prime, and you just, the equation, if you rewrite it, it looks just like what it's supposed to look, what we're looking for. All right, so that is theorem, what theorem is this? 2, right. That is theorem 2. So with all this done, we are now ready to prove the L'Hopital's rule. Okay, and the book spells L'Hopital with a S in there, so it looks like hospital. But the modern spelling nowadays in the calculus book, it spells without the S. Okay, so that is pronounced L'Hopital. And so let's prove the L'Hopital's rule on page 260. Theorem 3, f of x, g of x is in C1, okay, f, c, and g of c are both 0, so we have a 0 over 0 situation, and g prime of x is not 0 when x is not c, okay, that's important, that's an important part, that g prime is not 0 as long as x is not c on the entire interval. And then, and then condition 4, is the limit of the f prime of x over g prime of x equals to something. The a can be positive or negative infinity, that's okay, but they have to equal to something. That is, yeah. And if all that is true, then the limit of f of x over g of x will be equal to the same a, and that could be positive or negative infinity. Okay, now, so for the proof, we have the law of the mean, okay, from page 10 that we just saw, which is the g of c plus h is equal to, we can pull out the h and stick the g prime there, because the reason is because g of c equal to 0. So that's that. Then this, of course, proves that being the g, give me a second here. So when h is not 0, we are trying to show is that from this equation right here that we got from the law of the mean, and being that g prime is not 0 by condition 3, we know that g of c plus h is not 0. Okay, so we can divide by it. Therefore, the equation 4 that we had at the top of the page here, we can rewrite it with g of c on the bottom. Like this, okay? So we'll rewrite the equation 4, which is, let me see, why is it not looking right? I'm looking at the wrong page. Okay, so this equation, we'll rewrite it down here as a fraction. Being that g of c plus h is not 0, g prime of c plus theta h is also not 0, as stated here. And so we just said that g of c of h is c plus h is not 0. So these denominators are not 0, and we can rewrite this equation with the g's on the bottom, okay, and with the f's on top. And so then, and that works. And being the f of c and g of c is 0, so then we can write them as such. So we have f divided by, let me see. Yeah, that checks out. That is, f divided by g is equal to f prime divided by g prime. Okay, right from this equation on top. Right. And so, and once this is done, then we can let h go to 0 on both sides, and that will directly prove that the limit of f over g is equal to the limit of f prime over g prime. And we are done with the proof on the next page, as it says. Now, however, this does not, this theorem, of course, does not say that the other way is true. That is, but nowhere does this theorem say that if you have the limit of f over g equal to a, that proves f prime anything, which is I wrote down right here. Okay, the reverse proof doesn't work, unfortunately. And in fact, here's even an example of it. So consider this example. Why and check this example out to see why this is not the case. Okay, that is when f prime, that is this, if this limit exists, it doesn't necessarily prove that the other limit exists or any such thing. So please prove that yourself, as I have done here. If I can find it, page 261. Okay, I think it's right about here. Then, and down here we have that function that we have f is this thing and g is x. F is what? Let me see. F is, yeah, f, the numerator is x cubed, and then sine of x x to the power minus 1 right here, and then yeah, right here, and g is x squared. Then if you calculate f over g, that's well defined to be 0. But if you calculate f prime over g prime, then you'll find out that it ends up being something cosine 1 over x, which wiggles forever. Okay, so that shows why the I think it's called the converse. The converse doesn't work for theorem 3. So that is that. Next, there is example f and g. And please do those yourself as well. Let's see. I think I did that example. Where's example f? I guess I didn't do. Did I not do example for f? It doesn't matter. They're pretty easy, I think, and I mean pretty short. So as I did example g here, and the power stuff, it comes out and stuff. So please follow the book and do these yourself. All right, so the next, let's continue on page 261, where we consider the one-sided limits. That is, what if this limit is just one side? Well, that's easy enough. We can just rearrange the wording a little bit such that the one-sided limit, such as when x approaches a on the plus side or b on the minus side. And also, even if the variables are going to infinity, if x is going to infinity or minus infinity, that's fine too, because x going to infinity is just another way. We can just do a change that is the same as t goes to 0, okay, with 1 over t, and then we can, and which some quick manipulation will show that that is the same as the derivative for as x goes to infinity. So that's that. And then next there is example h. Please do that yourself. Okay, as I think it's also very short, as I have done here. Here's example h, which is just a one-liner, and so please do that. And we have come, I believe, the end of this section, and so we have homework to do. Homework is on page 262. Please do all of them. Problems 1 to 20, they are all pretty good. Okay, fun problems to do. And limits are usually quite fun to do. Okay, so please do all 20 problems, and when you're done, I want to talk about them. So let's talk about problem 1 on page 262. I think from problem 1 to 11, for the most part, they are very, very short, with the exception of maybe problem 9 is slightly tricky. So let me just show you what I did for your reference, and then I don't think you will have too much trouble with it. Here's problem 1, okay, and then 1, 2, 3, and then 4, 5, 6, 7, 8. And they're all very short, so I won't talk too much about them. And let's see, problem 9. The only thing is there's a cosine 1 over x in there that might make things weird. But all that needs to be done is we slap an absolute value in there and get rid of the cosine 1 over x. Once that's done, then things are much easier. Okay, so because the thing is going to 0 anyway, so once you prove the absolute value goes to 0, then by the squeeze principle, and the whole thing is going to be forced into 0. So that's problem 9. And I will also show you the different things that I wrote down that I took a screenshot of for problem 2. That is, I think I just typed, why is this in there? I think I just typed this into the calculator or something because I didn't want to do this by hand. Actually, yeah, whatever. The point is in there. And here's problem 3 for taking the derivative, okay? And it's easy for me to forget how to take the derivative of these things. You just slap on a natural log of the base, that's all. But I tend to forget it. And then problem 4, what is the derivative of arc cotangent? Who knows? But it's that thing. So, and also the derivative of arc tangent, they're the same. And so next, here is I even have a graph of it to show that it's going to, what is it, 0, right? Yeah, so that's just to show that it's going to 0. And what is the answer to problem 4? Limit is, well, who knows, okay? The point is that, why did I want to, it doesn't really matter. And next, problem 7, I have a graph here. That is arc cotangent x, and down here is arc tangent, and anyway, they have they go to something or something. Let me check. Oh, I know. What happened here is the arctan goes. This one goes to minus as x goes to minus infinity. It goes to minus pi over 2, and that one goes to pi, I think it is. So, and then you do division or something for problem 7. And problem 9 is the one we just did, okay, where I slapped on the absolute value sign and forced, because I plotted the graph, and you see what it looks like. So you know that it's controlled by the absolute value graph, which has the x-shaped thing. Yeah, so that's that. So next we have problem 10, which I calculate to be going to minus infinity. Okay, and I think there is no answer at the back for problem 10, but plotting it shows that I was right. So take a look at problem 10. After, on the other side here, after it's plotted, you notice that after it's plotted, you notice. Okay, after it's plotted, you notice that right here. It notice that it actually equals to this. The graph shows it going to negative infinity very, very fast. Okay, you can't even see the graph, it going down so quickly. It just it looks practically like a vertical line, even though it's a function. So that means my answer should be correct. And then problem 11 is a matter of taking, what is that? Well, anyway, problem 11, we have the thing calculated into, there is a big denominator here, and the denominator, yeah. Anyway, the denominator end up being positive for x bigger than 0 and negative for x smaller than 0, which means it goes to, on the positive side goes to negative infinity, and on the negative side it goes to positive infinity. And I plotted the graph of this thing here to prove that that is the case. And there's a little graph right there. Okay, that is problem 11. So next, let's consider problem 12, which is, let me see what it is first. Problem 12 is proving and figuring out what the limit of the sum of all that stuff is, okay? And there are two ways to do this. First, we go by the definition of the fourth derivative. And that thing might look familiar. That's because it is actually the fourth derivative of x. That is, if you write this out, is the fourth derivative, okay? And f prime of x is this thing. F double prime is that. F triple prime is this, and then eventually, and then the F fourth prime is equal to all this stuff. Okay, it's exactly like it says. But that is not what the book wants us to do. Of course, the book wants us to use the L'Hopital's rule. So by L'Hopital's rule, then we'll define A of h as the numerator, and whatever's on top of this, the original given equation, okay, which equals that, and the denominator will be B, we'll call it, so A of H is what's on top, B of H is what's on the bottom. And then we're trying to calculate what is the limit of A of H over B of H. Now to do that, so we apply the L'Hopital's rule. We'll take the derivative one time. We got that. And then plugging in as H goes to 0 is still in the 0 over 0 form. So we have to apply it again. Okay. So A double H over B WH, that we get that. And that is still 0 over 0. So we do A triple H. And we still get 0, 0 over 0. Finally, the fourth derivative, and we end up with that stuff. And then when we let H go to 0, but the denominator is no longer 0, see? So it's only 24. If we let H go to 0, the numerator end up being 24, 24f to the fourth x. So 24 divided by 24, so we have just one left. So that all works out nicely. But that is how this can be done with the L'Hopital's rule. Okay, I will put it a little closer so it looks better. So that is that is how to do problem 12, which is quite a bit of writing, granted, but not near as much as problem 13. Problem 13 has a ton more writing. Okay, now problem 13 is presented to us with a lot of writing. Stuff is already in matrix, and but we need to calculate this thing as look at the problem more carefully. You notice that H is to the power 3. Okay, and which means we need to take the derivative 3 times to get to the end. Now that is but this time notice that we cannot get away with what we did in proving the theorem, where we just take the derivative of one of them and call it done, because right now there's x in, we're taking the derivative with respect to and let's see, whatever we're taking derivative of, just let me see before I say something that's not necessarily correct. Okay, let me look at this. The derivative is h as h goes to 0, so we are taking it. Let me think. Right, that's what I thought. The derivative has to be taken with respect to h, okay? In other words, x is a constant in this differentiation process. But that would mean, but being that there's h here and h here in both rows, that would mean that you have to apply the product rule and has to apply it 3 times. Now, each time you apply the product rule, you double the amount of stuff, right? So the first time you have 2 things, and then you have 4 things, and then you have 8 things for each product. So that is going to add up fast. And that might sound like, wow, that is a mountain of writing. And that's what I thought at first. But there's a way to reduce the amount of writing you do. And so here's the problem, okay? And I will call the numerator h, a of h, right here. So the numerator will be called a to the power h. And then so the first we have, what is that? F. So this is by the product rule, the second derivative will be given by this formula. The triple derivative will be given by that formula. Okay, you can look that up online or just do this yourself. It follows the binomial expansion, being it's the same pattern. Okay, so first we know that a of 0 is equal to 0. If you plug it in, you'll find out that real quick. And so then. So we can apply the L'Hopital's rule. Now, to shorten the amount of writing we do is I'm going to let f to stand for f of x, and then f1 will be fx plus 1h. f2 will be f of x plus 2h. That way we don't have to write so many x plus 2h business. So that reduces the amount of writing we do. So then a prime of h equals to this stuff right here. Okay, and let's see, that's following what a of h is, and then as h goes to 0, we still have a 0 over 0 situation. So then a prime of h is so we take the a double prime of h, which equals to this, and each time we have to show that the a prime of h does equal to 0. A double prime of h, which is all this stuff here, okay, does equal to 0 as h goes to 0. And that's the reason for that is because as h goes to 0, the f1 and f2 are all the same thing. okay, because h goes to 0. Once the h goes to 0, they're just all f of x. So that's how the math is done here. Okay, I have it color coded to show the parts that cancel each other out and things like that. So all parts canceled out, okay, in the second derivative. And then next we'll do the third derivative. That's the last step. Now in the third derivative is this looks really difficult, complicated, and error prone, but it really isn't, because it follows the pattern. See, the coefficients are 1, 6, 12, 8, and then the subtraction goes backwards, 8, 12, 6, 1, and it does that every single row. Okay, so if you just follow the pattern, then it's much less likely to make mistakes. And this is the rule we're going by. You just directly follow this product rule and slap it in there and write all this stuff out. And what we have after the dust clears is that A triple H equals to this stuff right here that did not get canceled out. Okay, and so then A triple H over B triple H, where BH is just h cubed, as h goes to 0, will be equal to this stuff. And this stuff, you notice that in all this process, the 2 and 1 and all that doesn't make any difference, okay? Like G2 is the same as G1 and the same as G. The only thing that matters is all the primes. The second derivative and the third derivative, that's the only thing that make any difference in here, because we're letting h go to 0. So once this is all calculated, then we end up with this thing right here. And this thing is also happens to be this matrix, a neat little matrix where the first row is f, g, a, p, the second row is f prime, g prime, p prime, and the third row is the second derivatives, all nicely lined up. So therefore, it must be correct, okay? Even though we don't have the answer to this problem, the fact that the answer I found is so neat and clean means that it must be right. So we'll just trust that to be correct, okay? And if the answer is a mess, then I wouldn't trust it so much. But it matters that thing looks good and symmetrical and beautiful, even in math. So that is problem 13, sorry. And then next, we'll consider problem 14, where it just says they want us to change theorem what? Theorem 2 that has 3 functions. It doesn't say how or what or anything. So like how do they want us to change it, right? So I just plug 3 functions in there. So theorem 2 has 2 functions, right? So I let f of x equal to 2 different functions. So now we got 3 functions and plugged it in and then come up with this equation. And yeah, I don't know if that's what the book author wants, but it says 3 functions. Didn't say what or how, so that should be good enough. All right, so that is problem 14. Okay, next let's look at problem 15. Problem 15 is a matter of proving that something doesn't work. So we just have to illustrate it. By the way, the converse of P implies Q is Q implies P. I always confuse converse, inverse, contradiction, something. So I just looked it up so we know exactly what we're talking about. And so anyway, and to prove that, then we notice that limit of f, after some manipulation, we notice the limit of f of x over g of x does exist, because x is power 3 here. So it does exist and it's equal to 0. Okay, but the limit of f prime, by the time you do the calculations, shows that f prime it does not, over g prime doesn't exist. Therefore, the converse, my camera got tired and decided to not focus anymore. And so the converse then is false. So that's problem 15. Problem 16, so it being that the Rolle's theorem it only requires the f prime g prime to exist, then theorem 2, which is proved with the help of Rolle's theorem, can then be proved with a reduced requirement, as the same reduced requirement as well. Problem 17 says, and similarly, then theorem 3 it also works as long as f prime and g prime exists, because of problem 16. And then problem 18 is just a matter of calculating this limit, which we can do. Okay, first by L'Hopital's rule, and then by direct calculation, and that comes out nicely. And then problem 19 is again we calculate this thing. everything comes out nicely because G prime of C is not 0. That's the main thing. And then problem 20, f prime is 0 does not exist, and therefore number 19 does not apply on example E. 那么就是 say there. And that should be the end of this section.